Hold on, let me start this stream real quick and then I'll address that. Oh, that's awesome. Let me see how my audio sounds 1 second. It's good enough, okay. So, okay, and then as you can see my terminal, that works, yeah, okay. I am streaming on a new computer, so I hopefully don't run into any issues, but at least the stream will not crash like it did on my old computer, so that's good. Okay, so before I started the stream, we're kind of talking about how some of the challenges aren't yet released. They will be released tonight. Of course, that means that now this office hours isn't going to be able to focus on those unreleased challenges yet. If necessary, / it seems like it makes sense, I can potentially hold another office hours, maybe either tomorrow or on Sunday for an hour to address the new challenges. We'll kind of see, there's lots of questions and it makes sense to hold another office hours. I could probably go forward and do that. But for now, let's focus on the challenges that do exist. And also let me quickly ping the Discord just to make sure people know that office hours are happening right now. Okay. All right, let's get started then. What questions do people have for the currently released levels for Baby Race? Level 2 testing. Okay, let me start by launching that challenge. And then there's also a question, can we talk about using Python? My exploits have been all over the place. Yes. Level 3, how to change the win variable. Okay, we got all sorts of questions. Let's start by taking a look at level 2 testing. Let me launch it. I guess you can see my mouse moving, but okay, whatever, that'll work. Oh, right, I'm not sharing on Zoom. I don't... Is it possible for you to watch the Twitch stream on Zoom? Because I'm not exactly sure on this new setup how I'm gonna share to Zoom. Okay, that would be very helpful. All right, thank you. Okay, so we're going to be looking at level 2. Okay. Let me SSH into the instance. Okay, so if we launch Baby Race level 2 testing 1, of course we have to provide, actually, you know what, I'm going to work on teaching. I'm going to solve it in a testing way, and then once we have the solution, I'll move it over to testing. That way it is easier to explain what's going on. But once we have our working 2 teaching, we'll switch it over to testing. Okay. So if we launch it, we can see the challenge allows you to open a single file. And then this file will be opened and be sent to you, just like level 1. Challenge will verify that the file's path does not include flag. It's not a symlink. Okay. So if we, for instance, gave it like etc password, on the teaching levels, we of course do several blocks to make the timing attack easier. We just hit enter to get through those, and we can see that we called lstat on the path to kind of check to see if it was a symlink. In some of the later levels, we'll start calling stat, but it'll be on the directory. It'll be important to understand kind of the difference between lstat and stat. The high-level overview is that lstat will not follow the path if it's a symlink. It'll just like tell you about the fact, for instance, that it is a symlink. You can imagine that if you wanted to check if a file is a symlink, it would be very annoying if it followed the symlink, then because you could never then check if it's a symlink. So lstat lets us check if something is a symlink. Okay, and we can see that we can leak out etc password, probably not nearly as great as being able to leak out the flag. And of course, based off the description, if we pass it flag, path contains flag. Okay, so how do we solve this then? Let me start by launching tmux, and let's quickly go through the non-scripted solution to the challenge, just to kind of demonstrate it. So what we want to do is provide it with a path. Actually, let's quickly look at what needs to happen. So we provided it with the path /flag, and we can see that it's blocking until input. If we hit enter, it says the path contains flag. So we instantly failed there. But we can overcome that by giving it, say, home CTF A. And if we hit enter, the issue now is that it says, oh, I guess, do I already have that file existing? Hold on, let me switch to the other terminal and cd into my home directory. Let's just make a directory called race and start working out of this so it's a little more clear what's going on. Okay, so instead of CTF A, let's go with CTF race A. And if we hit enter, of course it tells us that we can't get the file status because the file does not exist. If we, however, make the file exist, so if we do like touch A, and now a file called A exists, if we run this again, we will see that it seems like we succeeded, because before we would break out, we did this blocking and then calling lstat and then it failed. But here we called lstat and then we're blocking again. So now if we hit enter again, presumably it just sent us the contents of A. Of course, since we have teaching mode set up, what we can do is that we can specify this A file. Here, we just finished checking to see if it's a symlink. We confirmed that it's not. And now if we switch back into our other terminal, we can remove A, and then we can make it be a symlink to the flag. So now we can see here that A is a symlink pointing at /flag. And we've already checked to verify that it's not a symlink, so the challenge thinks everything's good to go. We can read it out because it's not a symlink. And now we hit enter, and of course it gives us our flag. Now the question is, how do we do this without this very convenient blocking until input? We got to be very fast, and we've got to script it. So I could show you, I guess, how to do it from like a command line, like insane scripting, but let's just immediately jump into Python. Okay, so in order to do this, I'm going to make this terminal be Emacs, and this terminal will continue to just be here. And what we will do is we will, this is like going crazy on this large screen size. Hopefully it'll work. Emacs x.py. Yeah, I know what's going on there. Maybe Hold on, this is showing up weird. Yeah, it's showing up weird there as well. Let me just run it without my Emacs config. Oh, why it's, hold on, maybe it's not an issue. Maybe I'm confused. No, everything looks fine. The issue is that we're in tmux, and that's why we see like this double rendered bar. Yeah, okay, we'll just roll with this then. Oh no, once you start typing, it double renders. Hold on, okay. Let's do this. Although that also double renders it. That's annoying. I guess it's just a cosmetic issue though. Well, you know what? We don't need to be in tmux if we're going to do it this way. Yeah, let's just do it without tmux. That's the sane solution. CTF race x.py. Okay. In fact, we can actually just make our terminal appear here, and everything will be great. Okay. And we can reasonably well see that on the stream. Yeah, we'll roll with it. Okay. So if we do pwn.process of baby race, and we want to pass it a path that is going to be what it tries to read from, and we can pass it home CTF race A. And then we can do with pwn.process blah 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 as process, and then we can do process. Actually, let me run the challenge again so we can see what we want to block on. Home CTF race A. And we can see that we want to just like basically receive until blocking until input. Process receive until blocking until input. And then we want to send line like nothingness. And then actually the first thing we want to do, once we are blocking until input, we can go ahead and create the file. So what we want to do is import OS. And then we want to do OS open home CTF race A OS O create. I believe that is valid. Oh, we want, actually I think this is right. Let's see if this works. Okay, so we do not have an A file currently. If we run x.py, hold on, let's do it here. Let's make sure we know how to create a file. Oops, that is not at all what I wanted to do. I did create the file though, but let me run it from the command line. Why is this hanging? Oh, this is hanging because, oh, that's annoying. Hold on. Let's go with that. Python x.py. Okay, created our file. Good enough. Okay, so the next thing we want to do is we want to start scripting this. So let's remove that A file from there. Okay, so we want it to be created. The first thing is that A needs to exist so that it can stat it and check, or else stat it and check that it's not a symlink. So at this point it now exists. And then we want to wait for our next action. And our next action that we want to do is that we actually want to delete it. So we want to do os unlink home CTF race A. That will delete the file, and then we want to os.set symlink /flag to be home CTFA. And then what we want to do is send that and then process read all. I think that is the last block. And let's just print it. And we can decode it. Yeah. Okay. Python x.py. What? Hold on. Why am I so confused right now? Oh, lowercase p. Duh. Thank you. Okay. Python x.py. Okay, sweet. And we can see that the flag comes out. All right, thank you for the help. Okay, so this is, of course, in teaching, though. In testing, it's going to be much more tricky because we don't get to wait for these blockings. So how do we adapt our solution for that? Well, we can kind of think that two things need to happen here. In fact, let's kind of slightly restructure this in a way, and why I'm about to do what I'm doing will make more sense as we go on. Let me start by creating the file, and then right here we're going to call unlink as well. And the reason I'm doing this is I'm setting it up so that we have a looping structure, right? We want these two things to happen. If we assume that we start everything out with the file existing, for the first iteration we want these two syscalls to execute, and then in the second one we want these two to execute. And then also, actually real quick, I'm going to os.close this so that we don't like run out of file descriptors or something insane. We've got a finite amount, and if we keep calling open, I don't think, since we're calling it through os, nothing's going to call close for us automatically, and we should just clean up after ourselves. Okay, so this assumes now that we have a file, and then, in fact, we can try and also do the following. Just, I want to get basically the program into a state where it just works no matter how we run it. So let's just unlink it and then create it and then run through this. So let me do python x.py. No such file. Okay, so we need to handle if there's not a file. So if there's not a file, we can't unlink it, except file not found error. Actually, what we really, I think we just want to do this. Never mind. Hold on. Let's do it this way. And then python x.py. Then we don't even have to worry about that, right? Because we can run this multiple times just fine. No, we can't. We can't create it. Okay, so we try to do this, and then we accept permission error. Let's do os unlink in this case, and then create it. Okay, so this should put us in. All right, you know what? I'm overcomplicating this. Let's do just the try except. Let's just try to unlink it and then try to create it. And then no matter what happens, it will exist, rather than sit here and try and handle the correct exceptions. Let's just do something that will work. Okay. So now we can run this multiple times in a row, and whether the file exists or whatever, it should be good to go. Okay, so this initializes us into having our setup here. Okay, so now what we need to do is let's break this into the two steps. Let's call a function step 1 And let's say that in step 1, we want to perform the following action. We want to unlink, close, and that's, or we want to unlink, we want to create the file, and then we want to close the file. So instead, let's call step 1 here, and then let's create a function called step 2. And step 2 will do that, and now our exploit should still work. We've just replaced it with some functions. Okay. And now, what we want to do is now we're getting ready for our testing run where we don't have these blockings. But we're going to get ready to do the following. In fact, I will just start changing it. Let me copy all of this and comment it out so we know what we did that worked for teaching mode. And let's just readapt our script to testing mode. In fact, before we start doing that, let me switch into testing mode. Let's see here. Testing, launch. Okay. So we have our script. Again, now that we're in the new, we're in testing mode. Okay, and if we run our script, we will see that it doesn't work because it tries to, oh, well, that also doesn't work because we're running the wrong challenge. We're running teaching instead of testing. And then, okay, so let's see, this should again fail, and we're going to see that it fails because of an end of file. It's doing this receive until, blocking until input. Of course, in the testing version, that does not exist. And in fact, we can see that. Yeah, hold on. That is the wrong thing. Let's just manually type it. All right, whatever. Level 2, testing 1. Let's do it again. Baby race, level 2, testing 1. Home, CTF, race A. Oh my god, this is terrible. Baby race, level 2, testing 1, home, CTF, race A. And it, yeah, just immediately left. It basically just sent us the contents of A, which is an empty file. Okay, anyways, let's make this actually work. So what we need to do is we need a separate thread basically constantly alternating between step 1 and step 2. If we can make our program just constantly make it so the file system is potentially at the conclusion of step 1, which basically means that home CTF race A exists as some real file, and that the file system can also potentially be in the state where home CTF race A points at flag, then it's just a matter of chance on when, as the program executes, what the current file system state is as everything goes. Okay, so let's make it so that we are running step 1 and step 2 in a loop, basically. So if we do os fork equals 0, so fork is, it'll basically split off a child process, and in that child process, the value of fork will be 0 if it's the child process, and in the parent process, it'll be the PID of the child. So let's do if os fork equals 0. This is in the case of the child. And then we will do while true. And we will call step 1, and we will call step 2. So now we have a separate process, a child process that's executing for us, that is constantly just flipping the state of the file system as fast as it possibly can. I can't think of I mean, there's maybe a couple there's one optimization I have in mind of how we can make this faster, but let's assume this is good enough. So it's just super fast, alternating between home CTF race A not existing, in the case that if the file system at the end of this syscall, the file will just not exist, or at the end of either of these syscalls, it doesn't matter which, because closing the file doesn't affect the file system. At the end of this, A will be a real file, and at the end of this, the file system will be, the file system will be with A pointing to flag. So we kind of have three states that the file system can be in, and we're just running it as fast as we can to alternate between those three states. And we're just kind of basically hoping that the program catches it at that right time. That when it goes to check to see if it's a symlink, that we are at the end of this condition. And when it goes to actually open it, that we're at the end of this condition. And hopefully for neither of those two checks, it's in the unlinked condition. That's kind of what we are taking a chance on for this race. So if we run it enough times, hopefully that will just work. So let's start by clearing this out, clearing this out, clearing those out. And all we do is just read everything and decode. Okay, so if we do Python x.py, we're going to see that it only runs once, which is fine. And presumably it's going to fail. Where is it failing though? No such file. Okay. Unlink. Oh, wait, what? So we unlinked it, and then we created it, and then we get ready. So we do this initialization before we go into step 1, step 2. Hold on, let me run it again. Hold on. Let's just assume that the file doesn't exist. Wait, what happened here? What? I don't think I've ever seen question marks before. Oh, is the process running? Oh, we have it running still. Okay, let's just pkill Python. Okay, that makes way more sense. Okay, I didn't realize that I figured that when we killed it, that it would stop. Hold on, is that not true? PSaux. Hold on. What are these other Python? Oh, these other Python processes might be for my editor. PSaux. Yeah, let's just assume that it's done. Okay, so if I run python x.py, name except, oh, except exception. Okay. Do we have, don't think any of these are, but let's just pkill Python again for good measure. And then let's run python x.py. And then hold on. Now we do have Python still running. All right, I think something is up because of the way that I'm doing this. Okay, let's ignore, let's get rid of this, and let's just manually delete the file. Let's not be fancy, let's just manually delete the file before we run our script. Okay. So all we want is that, and then Oh, but then the issue here is that we need it to exist. But that's fine. We can make it exist before we delete it. So at the beginning, let's just do it in the child as well. Okay, so the child is going to create it. That way it can unlink it and everything will just make sense and we can just repeatedly loop through these steps. Okay, so if we do this now, why? Hold on, let me, how do I want to test this? Maybe what we need to do, I think the issue is that the main Python process is exiting, but for some reason this one isn't. Why would that happen? Okay, let's just be super lame and import time and time sleep 20. Then we don't have to worry about that, hopefully. pkill python again, python x.py. Yeah, maybe Python isn't the way. Maybe this. Maybe you're right. I don't know. This is feeling miserable. Okay. No such file or directory in step 1. How is that possible? We just created it. Right here. Home CTF race A. Definitely exists. Okay, let's not while true. Let's just do if true. Let's run it once. ps-aux grep python pkill python. Okay, let's also just get rid of this. Whatever, we'll pkill python if we have to. Still not entirely sure why we have to, because I would assume that when the parent dies, the child should be forced to die as well, but it doesn't feel that way. Okay, and then, so we pkilled python, and okay, so let's run it. Okay, finally we get something that makes sense. Error file is a symlink. Though what doesn't, oh, we just ran it twice because, okay, hold on. If we are the parent thread, we will execute this, otherwise we will not. Whatever, good enough. Because we can see that it just ran twice. And we can actually see that it interleaved the 2 executions of it, which is kind of interesting. Pkill python, and then python x.py. File is a symlink. Okay, that's what we expect. Okay, so now instead, let's make things work. Let's while true do this. Okay, it's RMA. Actually, hold on real quick. Yeah, let's just RMA. Okay. If we now run this a bunch of times and look basically for results equals this, to make this be the result, and if, what is it, pwn, or is it, if, let's just say if pwn in result, that should be sufficient. We can print the result. And then we can break out of this loop. Okay. And oh wait, how is this? The step 1, step 2 shouldn't be there either. Highly confused about that. Okay, so hopefully this is beginning to make sense, even though everything's becoming a disaster. Okay, so you say it's pwn_college. Yeah. That sounds correct. Let's just make it slightly more clear with that. With pwn_college in result. Okay, so what we're doing now is that we have a child process that is repeatedly symlinking, unlinking, and making that path be just a normal file as fast as it possibly can. So the first time through, it'll delete the file. and then it will make it be a normal file, and then it will delete the file, and it'll make it be a symlink. So we're just constantly alternating the file system, and now we are going to constantly run the process. So we have the file system rapidly being altered as fast as possible. We have the challenge process being run basically as fast as possible, and we're waiting for the right interleaving of events to occur. So now if we run python x.py, we begin await. And boom, pops out. Didn't take too long. So when the parent dies, does the child. So that's what I thought, but for some reason we're seeing it still existing. No, so it's not all of these user bin pythons. I think that's my editor, and I don't know why my editor is going out of control. I'm sure there's some Emacs memes there. But the second to last one, python x.py, still exists, which doesn't make sense to me, because this isn't like, it shouldn't be like a daemon or whatever. Let me think here. I'm trying to think about our verify scripts. Maybe it's not an issue for our verify scripts that this keeps running because we just kill it anyways. Huh. Like we kill a whole container that's verifying that it works, which will definitely kill it and not just continue to waste resources. Okay, whatever. We can actually overcome this very easily. What we can do is the following. And it's not really something that needs to be overcome, but let's show how we can handle this and not make it so we don't have to keep calling pkill python. Let's say that pid equals that, and then the child process will be if pid equals 0, and then in the parent process we now have the pid. And what we can do is at the end, we can just do it outside of the loop, os.kill os.kill, what am I thinking? The PID, and then the signal we want to send, let's just send a 9. And this will kill, that'll make it so that we can clean up after ourselves. Or you could os.system pkill python. Yeah, that's also a solution. Hopefully this one is slightly more, less nuclear. Okay, so if we run this now, let's just see if we're cleaning up after ourselves. Clearly we already got the flag, so I mean, you could just destroy the container and be on your way, and maybe you don't care about cleaning up after yourself. But let's just show that we can. Okay, now if we grep for Python, we can see it's only these, oh no, wait, we don't see, we see that there is a Python. Hold on. Let me pkill Python one more time. Maybe I didn't kill it before, I don't remember. ps aux grep Python. Okay, so it definitely doesn't exist now. And now if I run python x.py, wait for our flag. Okay, ps aux grep Python. Okay, I think that's a good sign, right? ps aux, there's no Python. Okay, we cleaned up after ourselves. The other thing though is if we want to even more correctly clean up after ourselves, we need to handle the condition if we like kill this because we give up or whatever. Like if we like rapidly hit Control C right away rather than like letting it finish, we can see that ps aux grep Python. Wait, but that didn't kill it. I don't understand what happened there. Hold on. But what I was going to show is that you can do this try finally. Maybe it's not such an issue, but you can do a try finally. And what's going to happen here is that in this block, if we receive our sig kill by hitting Control C, this finally block will still execute. So that would also allow us to clean up after ourselves. But either way, maybe we are rambling too much about how to clean up after ourselves, and this still just works anyways. Let's verify that this still just works anyways. Very slowly. Getting very unlucky, unless I... Yeah, Yeah, I can talk about that. I'm going to talk about 3 first because there was a prior question on that, but yeah. Okay, why is this not finishing? Hold on. So something that might actually speed things up, potentially, is if we do pwn context log level equals critical. So basically just turn off all of pwn.tools logging, which is potentially due to buffering, slowing stuff down. Okay, right, we can deal with that. Let's rm a python x.py. And it instantly comes out. You know what happened? I think when we had our try finally, oh no, this try finally is still here. I think what happened is that we hadn't cleaned up our home CTF race A file, and since the file existed, it was an issue. And we can see again, we can just run it super fast and it just instantly pops out. Yeah, we just have to make sure that this A file doesn't still exist, because if we run it now, because A does exist, we are going to run into an issue. No, we won't. We'll only run into an issue if it's a symlink, I think. I don't know. Make sure the A doesn't exist. Okay, so anyways, enough talking about cleaning up after this code. Let's take a look at 3. So 3 is slightly different. Let me launch the challenge. It's a Sitchin. And if we run it, okay, well, let's start by just giving it like an etsy password. We can see that this challenge will verify, again, not flag, again, not symlink, but this time it checks to see if the file is less than 256 bytes. And it tells us also, I guess that's all it tells us. Okay. Oh, it's Etsy, oh no, it's too large. Okay. So we can see the Etsy password is too large. Makes sense. Etsy password takes more than 256 bytes. Let's do home CTF. Actually, let's just go to home CTF race. Let's create file A. Let's do baby race level 3 teaching 1, home CTF race A. And we can see that it's calling lstat, and it seemed to not complain because we're blocking again, getting ready to continue. And it tells us at the end the value of the win variable is 0. You should be thinking kind of back to maybe some of the baby mem levels when you hear win variable. So this win variable exists on the stack. In fact, if we do an strace of this, we can see that we called lstat, and we can see that it in fact called lstat, and then we're blocking again. And then we can see here that it read in 4096 bytes. And maybe you're thinking, hey, but the size limit was for 256 bytes. Maybe the buffer is 256 bytes. And if you reverse the program, you will in fact see that the buffer is about 256 bytes, and that immediately after it is a win variable, but we're reading in 4,000 bytes. And of course, now you get to exploit via this timing or via this race condition issue, because it kind of thinks that there should be only 256 bytes, but then it goes in and reads up to 4096, and suddenly there's not just 256 bytes in there, there's more, and you can overflow. My webcam is frozen. How did that happen? Huh. What happened? 1 second. Well, that's terrifying. Hold on. Okay, my audio's back now. That still is broken. Oh, well that works, except it's like taking up all of the screen now. But it's still frozen, isn't it? Well, that's lame. All right, whatever. We'll just remove that from happening then, for now. Well, for this office hours. I will look into it later. Very sad. Okay. We will move on. So, looking at level 3, as we were talking about, we are checking if it's 256 bytes. If it's not 200, or if it's less than 256 bytes, we continue. But due to erasing it, we can then make it be more than 256 bytes, and then when it goes in and reads it, it can overflow its buffer. So that's kind of the general idea of 3. I'm not going to go into directly solving it on stream, but that is the idea. Okay, so, and then there was also a question about level 5. Okay, getting past level 5 testing seems tough, even though my exploit is in x86 assembly, and I'm using a file system maze. Anything I can do to win the race against the binary. Okay. So I will start by saying that you don't need to write assembly yourself. Using Python is sufficient, let's say. The verify scripts use Python and it works just fine. Okay. How to make it faster. So there's a number of things you can do in the case of 5. In order to make it faster. Part of it is going to be just make sure you run it for long enough. There's a chance it's slightly more complicated because you need to account for being able to have your program or your file system be in an additional state. So you're kind of, instead of needing to alternate basically between 2 states that the file system can be in, you have to alternate through 3. Okay, let me SSH in. And this is this makes it a little more tricky. So let's first though see what does level 5 do. And again, we need to pass it a path, home CTF race A. Okay, so we can see the file will be sent to you. No flag, don't make it symlinked. The challenge will verify that the directory the file is in is owned by root. Okay, so this is a new constraint. This means it's going to be looking at the directory of our file. So for instance, when we pass home CTF race A, it is going to be looking at home CTF race. And verify the directory of the file is owned by root, and that other users are not able to create files in that directory. So for instance, that would make the root directory work because the root directory is owned by root, and it is not writable by other users. This would also mean that, say, the /root directory, in fact, I can't even view it, but we can see here that this is also owned by root and not readable by other people. But something that wouldn't work is /temp. /temp has the issue that, where is it? Temp has the issue that other users are allowed to write into this directory. So it basically is trying to, again, defend against race conditions in a new way. And the way that it's doing that is basically saying I will only look at directories which are owned by root and other users aren't able to write in, which basically means that our user theoretically is not able to make files in that directory in order for it to pass. Okay, so we can, of course, overcome this. And the way we overcome it is using race conditions. So the first thing that's going to happen when it goes through and checks, maybe I should run this in tmux again. Run with this, home CTF race A. Let me create a second terminal. We can go into home CTF race. We can see that A already exists. Let's just delete it. So it's currently blocking. It's going to be checking if A is a... actually, maybe it'd be easier to show exactly what it's doing using strace. I guess, though, it happens after. So if we hit enter... let's just run without strace. Let's just describe what's happening. Okay. So it's checking to see if the file exists here. So we're going to fail here because it fails to get the file status. And that's because A doesn't exist. But if we make A exist, we can run it here and we can hit enter and we get past that. We called lstat, not following symlinks. And so basically, it seems to have worked. And then we're getting ready to call stat. So whereas before we're calling lstat on the entire path, now we're calling stat on the directory. So actually, let's switch to strace. If we hit enter, and then let's hit enter again, we can see that right here, it basically removed the /a at the end. And it's just looking at the directory. We're doing the stat on that. And then we can see, let's just run it without strace. If we hit enter and then enter again, we can see error directory not owned by root because home CTF race is not owned by root. But something that's useful for us is the fact that stat is going to follow symlinks, which means that if we make, let's say we create, let's remove A, and let's make a directory inside of race called A. Okay, and then we go into A here and we create a file A. Well, now what can happen is, as we're blocking again until input. Actually we didn't run it with /a/a. So we're blocking until input. It's happy with our path we gave it. The issue now is that we're about to see if home CTF race A is owned by root, which of course it is not. We want it to be owned by root. So how we can do that actually is that we can remove the file A, we can come back up, we can remove the directory A, and then we can symlink /say root to be A. Symlink not found. Oh, link.-s, oops. Link -s, okay. So now we have this A directory, which is pointing at /root, and because we're calling stat, it's going to follow that link. And then it doesn't care like /root contains a file A, because we're just looking at the permissions of the directory in this case. So now if we hit enter again, we can see that we just passed that check. And now, once we hit enter again, it's going to read out our file for us. So we need to make it correct again. So we want to remove this symlink, we want to make dir A, we want to enter A, and we want to link this A to B to flag. And now, if you were to do, and it's not going to work for us because we're not suid, but if we were to do homectf race A, it would be printing out flag. And we can see, in fact, if we do ls-al, it's pointing at flag. So now if we hit enter, it gives us our flag. Okay, so that kind of demonstrates what's going on in terms of how you exploit this, at least in teaching mode. The question now is, how do you make this as fast as possible in order to beat the race? Okay, so if I'm going to start by leaving tmux. If we emacs homectf race x.py, we need a couple of things to happen. So let's switch there. Actually, let's stick to teaching for right this moment. And then let's give it homectf race A/A. And then let's read until blocking, I think is what it says, right? Blocking until input. And then once we're satisfied with the state of the file system, we can send line. Okay, so what we want to do, we're going to have basically 3 steps. So let's just call step 1 initially. Let's call step 2, and then let's call step 3. Okay. And step 2, step 3, and let's set up what we want. So we want homectf race A to be a directory, so we can do make dir. And then we want, what else do we want? We want to create a file, which will be /a/a. Okay, so this puts us in a state where we can confirm that this is not a symlink. Okay, and then what we need to do is we need to unlink A/A, and we need to rmdir homectf/a. And then we want to symlink homectf race A to point at, let's say, root. So that should satisfy what we want the state of the file system to be in for 3, for the second step. And then for the third step, what we want to do is we want to unlink homectf race A. You don't call rmdir because it's a symlink. You unlink symlinks, even if it's pointing at a directory. So we unlink homectf race A, and then we want to make that be a directory. And then we want to symlink that like this. And AA, okay. And this is all that needs to happen. Okay, let's get rid of this just to verify our stuff is working. Let's just put like an if false. pass. That way our structure of our program is still ready to go. And then we call step 1, we call step 2, we call step 3, and we see if we were correct. Okay, so let's go ahead then and run it. Actually, let's start by making sure that A doesn't exist. RMRA. Okay, now if we run it, we cannot read until, oh, whoops. Process. And we can make that not happen. Okay. Okay, we can see that our approach is working. If we now go ahead and RM, yeah, okay, yeah. If we RM A or RM RA, we can run it again. If we don't RM it, we are in an invalid state, but that's fine. We'll just make sure we RM A before we start everything. Okay, so we're getting close. Let's see here. Now what we want to do, in fact, let's just delete this stuff. Okay, if we want to put this in a loop. So the issue now with this entering into a loop is that what do I want to do? So we can see that this is the current state of the file system. We'll have a directory A and we'll have a symlink. So we need to unlink in order to loop around, we need to unlink AA and we need to rm dir A. Okay. Let's actually just manually add in our final cleanup steps. Let's do step 3 now, and then, actually no, let's do it right. We want to do the following. This is what it's going to look like anyways, because this is what the state of the file system is at the end of 3. So let's just do that at the beginning, and then let's make it so step 1 cleans up. So OS unlink home CTF race A, and then OS rm dir home CTF race A. Okay. Now if we run this, unlink permission denied. Oh, right, because we're not running in testing mode. Okay. Let's just make sure our solution still works before we jump into testing mode, because it would not be great if it didn't. Okay, Python x.py. Wait, am I something? Oh, we're not. We started. I see. We started our thread. Yeah. So what we need to do is we need to comment this out again. Okay. That's from Python x.py. Okay, so our solution still works at a high level. Now we want to make it be. Now we want to make it work for testing. Okay, so let's leave this. Yeah, just exit. Let me switch into testing mode. And now let's go ahead and Emacs home CTF race x.py. Okay. And then let's go ahead and set everything up. Okay, so if PID equals 0, right. Oh, whatever I did before didn't fix it, did it? But this is fine. Okay, so we're getting ready to create our background process that's changing our file system. And we can get rid of this. We can get rid of all of this. And we can do that. And we can do that. And let's just say that's irrelevant now. Okay. So in theory, this has the ability to work. Potentially, it's very unlikely for it to work, but it at least has the ability to work. So let's see, maybe we just get lucky and it works. Oh, right. Not quite have the ability to work. Almost has the ability to work. If we change this path to be correct. And we should RMA, make sure that's gone. Okay. Now if you run it, let's see if within, I don't know, maybe we give it like 15, 20, 30 seconds, I don't know. Maybe even up to a minute, but we're not going to. See if it spits the flag out. In fact, we can see if we do, oops, how do I want to do this? Oh, that doesn't work like that. One second. We want to do this. Let's make another terminal. Okay. And then if we just look at this, we can see that it's rapidly doing stuff. Yeah, I think it's going crazy. But we've been running for a while and it's not working, so maybe it's not our lucky day. So let me close that. Let's kill that. Okay, so this seems probably not fast enough. We have a lot of things going on, right? We've got like 5 syscalls happening here, and we have 3 syscalls happening here, and we've got 3 more syscalls happening here. That's kind of a lot of syscalls. And if you think about what is involved with our race, every step of the way, the process is basically going to execute a few assembly instructions, maybe not so many. But really, the amount of overhead that is contributing to our chances of winning is basically it calling one syscall. So we need our, like, in this case, like 5 syscalls to execute at like this insane rate. It's basically, this is too slow. We want to make it as fast as possible. And there are tricks that we can do to make it faster. Beyond just this, what Giannis talked about with the maze and like nice square. I honestly haven't looked at those things yet. There's things we can do just in our solution itself with the syscalls that we're calling to make it significantly faster. The faster we make it, probably the faster or more likely it is that we're going to win. Okay, so how can we do that then? Well, what if we use more symlinks? So here we're like closing and opening a file. And then like we're making a directory here, and we're just calling a lot of things. In theory, we could have our file system set up to be ready for us. So what we can do is that we can make, let's say, let's make dir homectf race, let's just call it B. So this exists as a directory now, not a symlink or whatever. And then let's go ahead also and create a file inside of B called A. Yep, okay. And so now we have a directory B that contains this file A. And then let's also make a directory C. And C will contain a symlink to the flag. Okay, so now we have B that already has a real file that'll pass the first check. We have C that has our symlink to the flag. So what is left? What is left to clean this up? What's missing is our directory A. And all we want A to be now is let's just make A be a symlink. Let's make A be a symlink to either B or C. Or to /root, also to point out, because we need, this only sets up 2 of the 3 states that we need the file system to be in. The third is that we need A pointing to root, but that is also just a symlink. Okay, so let's go ahead and unlink /A. In fact, also let's go ahead and os.makedir homectf race A so that it exists when we go to unlink it. Okay, so if we unlink A, and then what we want to do in the first step is we want to symlink A, os symlink, that's probably not exactly what we want. We want to symlink A to B, homectf race A. Okay, so after this, so we unlink A, so A no longer exists, and now A is pointing to B. And what is at B? So let's actually just comment here. So we have race A, and let's say A because this is the file that's always trying to be accessed. Oops. And this is pointing at homectf race BA, right? Because we just made homectf race A be a symlink. Okay. So this works. And then the next thing we are going to do is we are going to unlink A again. Or I guess this will be in the step C, or step 2, sorry. We are going to make A point at C. Sorry, not C. We want, in the second step, we want it to point at root, because root is owned by root and is not writable by other users. Okay. And it's going to follow the symlink, so that's fine. And the final thing we want to do, actually let me copy this one. So we can say now like homectf race A points to /root, which is going to pass that check. And then the final thing we want to do is point at C. And now we're going to have like homectf race AA pointing at homectf race C A, which is going to be pointing at home, or it's just going to be pointing at flag. Because we set up our symlink here, homectf race CA points to the flag. And yeah, okay. So let's see if this works then. We have the conditions that A, B, and C must not exist at the start of this. So let's make sure those don't exist. And let's see if we win. Something went wrong. Hold on. Oh, I think I know what went wrong. Hold on, let's make sure that Python is not still running. I think what went wrong is, where are we calling unlink? Okay, so the issue is that unlink doesn't work against directories. But what we can do is, in this state, we can rm dir A, because actually no, because this will be a symlink here. It'll always be a symlink, actually. So what we want to do, this is fine. We just need to fix how we create it at the start. We need this to be a symlink at the start so that we can just unlink it in our step 1. So we want this to be a symlink to, I don't know, let's just say to root as well. Why not? Okay, so now we can, now this is unlinkable. So now we can just call unlink, whether it was in the initial state where it's pointing at root, or whether it's at the end of step 3 where it's pointing to race C. And now A is always going to be a symlink. Okay. Oh, did I forget to kill stuff? RMRA, RMRB, RMRC. And now we see if the flag shows up. Yeah, I can confirm that these are solvable without the mazes. It's very possible, though, that the maze would help. Yeah. Okay, maybe it's worth running more instances of this. Let's just really hit the server hard. Hold on. Maybe it's a bad idea, but let's go for it anyways. Let's close out of this. Okay, ps aux. Okay. Python, or let's get this home ctf race. That's rm RA, B, C. Okay. And then what we want to do, I'm just kind of guessing here. Okay, first let's start by running it, making sure, yeah, that doesn't help us. Let's make sure that's cleaned up. Okay, RMRB, RMRC. Okay, so let's, actually real quick, let's change some of our logic so that we can multi-process on this pwn.process thing. So let's go ahead, let's even get rid of this forking mechanism. Let's go ahead and make a y.py, and in y.py all we're going to do is the following. And we're going to create steps 1 through 3. And then we need to import OS. Okay, so now this is going to rapidly, this will be basically the thing that's changing our file system. And then let's make z.py. And let's make that be this logic. And we need to import process. And yeah. Actually, let's make it so we do our forks here also. Let's do, hopefully this isn't too crazy. Let's go with os fork can actually just call fork a few times, and each time it'll double the number of things doing this. So this means that there's 2, this means there's 4, this means there's 8. I don't know, let's go up to 16. So this means we will have 16 different baby race level 5s running at the same time. Okay. Let me do that. Let's launch into tmux so that we can analyze what processes are running easily. And I'm going to create a new terminal. In this one, I'm going to run y.py. Okay. And then here we can see that insanity is happening with the file system now, which basically just means where A is pointing. You can see it's just moving all over. Okay, so that's running correctly. Now, if we do python z.py, maxq z.py, did I not save this or what happened? Oh no, my terminal is just being insane. Hold on, let's kill this real quick. Let's leave tmux, unfortunately. Emacs z.py. This needs to be import pwn. Okay. Let's just make sure this runs. Seems to do something. Emacs z.py. Did we get rid of that critical message? Yeah, let's make the critical also. Make the log level be critical. Okay. And now let's do ps-aux. Okay, we're good. Let's run tmux. Let's run python y.py. Whoops, we need to rm ra rb rc. Oops. And then let's do python y.py. Okay. And now our file system's rapidly changing. And then let's go ahead and do python z.py. Okay, and then let's look at what processes we have running. Okay, so we have a ton of z.pys running, which 2644, which is running some number of baby race level 5. Let's see if we can see the file system. So we can definitely see that, actually, let's make sure that B looks correct. So B is pointing at A, which is just a file. And then C is pointing at flag. And then A is the thing that's constantly alternating. So that showed that it can point to B. That just showed that it'll point to C. And that just showed that it'll point to root. Okay, so everything is in order. The question is, what's happening? It's possible that if we just keep leaving this running for a bit, that we'll get our solution, as unsatisfying as that might be. Let me try and think about what's going on here. I may have to readdress what's happening in like a next office hours, but let me see if I can think about this. I'm not really sure why this wouldn't work. So something that we can test is if our current approach still works in teaching. I think it would. Oh, that guy just got killed. Okay. It's actually kind of surprising that it got killed. Trying to think. So one other optimization we can make is the following. Let's try it. I'm not exactly sure about it, but let's see what happens if we do the following. Let me close out of all of these. Okay, let's change y.pi to do something else. And what that something else is going to be is the following. We're going to make a y2.pi. And y2.pi's only responsibility is just going to be to call unlink. All it will ever do is unlink A. And now, instead, what we can do here is just try to do this and accept exception pass and basically repeat that for all of these. I'm not exactly sure if this will make it easier or not, if this will actually help our solution, but let's give it a try. Let's unlink. Okay, so all we're doing now is just trying to symlink. And instead, the person that's going to do the unlink is going to be a separate process. So this potentially can make us, under the right circumstances, like twice as fast, in theory, because if we interleave y and y2 such that y2 correctly calls the unlink before this guy calls symlink, or whichever person that needs to call symlink calls it, there's a chance it can work. I'm slightly skeptical of the idea, but let's see what happens. Let's rmrb, rmrc, tmux. Let's run Python. Let me just make sure that everything looks correct. Yep, all we're doing is symlinking now at y2.pi. And all we're going to be doing here is just spam unlinking. Okay, so let's create a new terminal. This terminal is going to call y.pi. And then let's create another terminal. And this is going to call y2.pi. We need to add an exception there as well. Let's leave tmux real quick. Okay, so this is going to run now. And actually, if we look at it, we should see that A is not changing. It'll always be a root because no one's ever unlinking it, so the other syscalls that are running in Y are failing. But once we add our unlinker, now stuff is unlinking. So let's see if we can verify that stuff is changing. So A is occasionally pointing at other things, which seems to be exactly what we want. Root B. Okay, does it ever point at C? I'm sure it would because there's not really a reason it would point at 2 but not the third. But let's see if we can find it. And it points at C. Okay. So now, and how many processes do we have running? Wait, how is z.py still running? Kill z.py. I don't know what the deal is with that. ps aux grep. Alright, let's just look at what's running. Wait, what? pkill. How do I specify this? Okay, let's just pkill Python. Okay, which means we need to relaunch y.py, which means that we need to remove A, remove B, remove C, and then we need to python y.py, python y2.py, see if we see A changing, seems to be changing, okay. And now let's run python z.py. Okay, somehow, okay, amazing. This is incredible. You know, I was actually highly skeptical of this idea. It came up with it on the spot. And somehow it actually works amazingly. That is, I love to see that. Okay. So let me try and explain why, even though I was skeptical of the idea that it works. The idea of what we were going for with this approach of having basically this y.py and y2.py split into two separate things. Actually, maybe it'll be easier if we, let's just pkill Python, okay, and let's leave this. Okay, let's look at our solutions. Again, let me try and explain why, even though I was skeptical of it, it works. So the idea with this solution is that as we are running through, wait, what? Oh no, we were running z.py, okay. Okay, so as we were running this, so we do fork 4 times in a row. That just basically means we're gonna parallelize out to 16 attempts. Basically, we're gonna have 16 processes running this concurrently, just increasing our odds. And all we're doing is just praying that whatever the state of the file system is as the program runs and moves through is correct. So what is the thing that's changing our file system? So we have y and y2. So in y, all we try to do once we set up how everything works, and basically that means making b slash a be a real file and c slash a point to the flag, and then just the idea now is that in step 1, step 2, and step 3, we're just changing what A points to. So in this configuration, A points to B. In this configuration, A points to root. And in this configuration, A points to C. So we're just hammering through this as fast as possible. So before, what we had is an unlink right before we would do this. But that, in theory, is going to take twice as long, right? Now you have to perform 2 syscalls. You have to perform an unlink and then a symlink, and your process can only execute 1 syscall at a time. But if we split that out into a y2.py that does the unlinking, this guy is just going to spam try to unlink the file as fast as it can. But now we have 2 processes altering our file system. If we're kind of like almost racing y and y2. This is like a whole nother dimension of racing. We've got y and y2 racing each other to set up the file system in a way that even makes sense. So we're basically hoping that this unlink gets called, and then one of these symlinks gets called, but it's happening in two separate processes, which means that we could, in theory, enter the kernel concurrently from two separate processes and perform the process of unlinking and symlinking simultaneously. And depending on what kind of locking mechanisms exist in the kernel to determine what happens, we could get lucky enough where even though both are executing in the kernel at the same time, the unlink goes through and then the symlink goes through. But we don't have to pay the double overhead of entering the kernel back to back. We can do it like simultaneously. And that's kind of the idea of this approach, and it looks like this approach actually works. If anyone has any questions on that, I can try and explain. But it looks like this is looks like a very good solution, in fact, for making the testing variance work for 5 and, as it turns out, also 6. There's going to be a slight twist on 6, but I'll probably let you guys look at that. Okay, any final questions? I'm going to start wrapping up office hours. Yeah. Yeah, you could probably mute the audio on the stream. That's probably the... Yeah, that's the basic idea, that you split off into separate processes. So we have, for this solution, we have z.pi, and all z.pi's responsibility is to just run baby race level 5 testing 1 with home CTF race AA as the argument to it, and basically just see if the flag was in there and print out the flag if it was. That's all it does. Well, that and fork to 16 times so that it's running this all 16 times. But then there's y.pi, and all y.pi does is it tries to symlink in 3 different ways. You, in theory, I guess, could split each attempt to symlink into a separate process, but I don't think that would help you. I don't think. I think it's not. Maybe it might even hurt you if you were to split these symlinks into separate processes. I'd have to think about it more. But all y.pi's responsibility is to attempt to symlink A to a directory. In the first case, it's to symlink A to B. In the second case, it's to symlink A to root. And in the third case, it's to symlink A to C. And we've already pre-set up so that B and C are configured in a way that it's going to pass the condition, pass the check. So we just have to get one syscall through. We just have to get one syscall through in order to make the file system be in the right state. But we also have in order for these symlinks to eventually go through, before you can symlink, you have to unlink. And we, in y2.py, call just unlink as fast as possible. And we split y2 and y into separate things rather than do like os.unlink here, which is what we had before and it wasn't working. Rather than do this, this is, in theory, like twice as slow, right? Because you need to enter the kernel twice. So you have to kind of think about how much time things take. And doing a syscall is actually an expensive operation. It takes time to enter the kernel and to context switch and to context switch back. And that's basically what we're racing against, right? The challenge program is just making some syscalls, and we have to beat those syscalls with our syscalls. So we want to be as fast as possible. We don't want to do these in order. We want to do them at the same time. Like that, apparently, I was suspicious of the idea, but that seems to actually work really well. So rather than call them in order, which didn't work for us, we just call them at the same time. And it works. It's great. All right, any final questions? Yeah, the idea of the teaching ones in this module is to make sure you understand what sequence of events needs to occur, but you don't necessarily care strictly about being super fast in order to perform that. Because that's the blocking just means you can kind of set everything up at your own speed. Like you can just do it all even without a script. But then the testing is like, yeah, you need to be ultra fast. Yeah. All right, I am going to end this office hours. Thank you everyone for joining. We will post the additional challenges tonight. Yeah, there's another question. Go for it real quick. Okay, so the maze I'm not gonna be able to answer. You might have to wait for Jan's office hours. I haven't done anything with the mazes before. I, I mean, honestly, I'm skeptical about their idea because the kernel seems like it should be able to go through it fast, but I don't know. Jan says it works. I don't know. I would potentially wait for his office hours / message him to do the maze, but I can definitely confirm that it is solvable without the maze as we just demonstrated here. On the other hand, it's possible that the maze will be conceptually simpler to you than what I'm doing and that the maze will in fact work. But I can't say anything about the maze because I don't know enough about it. Yep, okay, I am going to end the office hours. Yep, see ya.